Hello everyone! So, you just have watched the long video about the inner product. Yes? And now I'm going to do a quick summary of what is important, what is the takeaway from that video. Okay? Now, before we start, so I think this is the first time in your education of maths that instead of being told, okay, this is how you do this operation, and you are given examples, and then you think, and what are the properties of this operation? That's how you normally have studied things. You first study how it's done, and then you study the properties. Here, we have done it differently, and this is much more profound. So we have first introduced the inner product by telling you what are the properties. And once you know the properties, I told you, okay, so these are the properties. Anything you find that fulfills these properties or complies with these rules, that will be a valid inner product. And this is very powerful because it depends on what the vectors are. If you are doing vectors in three-dimensional space, real vectors, then the inner product could be the dot product, which you already know. But if you were working with, for example, functions as vectors, which is something, as I said earlier, is outside of this module, but you will be doing it. So then the inner product between functions is not a dot product, it's something else. Yeah. Okay, having said this, let's revise what were the axioms of the inner product. And I'm going to go directly to the Hermitian inner product because that's the most general one. Okay, the Hermitian inner product is the one that we use whenever the vectors are complex vectors. Okay, so there are three axioms. So the three axioms are conjugate symmetry, and conjugate symmetry means that the inner product between two vectors a and b is equal to the inner product between vectors b and a, but doing the complex conjugate of the result. So remember, the result of the inner product is always a scalar. It's a number. It could be a complex number, yeah? So that's why when you flip a and b in the inner product, you need to take a complex conjugate. That's called the conjugate symmetry. Then it also has the axiom of positive definiteness. And this is saying that the inner product of a vector with itself always has to be bigger than or equal to 0. Yes? And finally, you have the axiom of linearity in the first argument. And what this means is that if you do a linear combination of a vector alpha a plus beta b, and you put that as the first input of an inner product, so you do the inner product of that linear combination with another vector c, then the result is a linear combination of the inner products alpha a with c plus beta b with c. That's the linearity in the first argument. Now it's interesting because if you combine the axioms 1 and 2, then you arrive to what you could consider a new axiom, though it's not really an axiom because it is derived from the others. But this new axiom would be conjugate linearity in the second argument. And what this means is that if you do the inner product between a vector c and a combination alpha a plus beta b, then you can apply the linear combination to the result, to the inner product, but you need to do the complex conjugate of the coefficients. So you need to do alpha conjugate times the inner product of c with a plus beta conjugate times the inner product of c with b. Okay, so don't forget that if you are applying linearity on the second argument, you need to do complex conjugates. Now I have a quick note to make about this. So this is the choice that linearity has to be in the first argument, and therefore complex linearity is in the second argument, is an arbitrary choice. So mathematicians can choose whatever they want. They can say that the first argument is linear, or they could say that the second argument is linear. If you said that the second argument is linear, then applying the conjugate symmetry, that would mean that the first argument would have conjugate linearity. And that's what physicists usually do. So in other words, mathematicians and the books written by mathematicians usually use an inner product in which there is linearity in the first argument. However, physicists, as you will be doing in following years, you will be using an inner product which is linear in the second argument. Okay? So I just wanted to point that out because when you are seeing the inner product later, you will notice that. So let me write it down. In physics, linearity in second argument, which implies conjugate linearity in the first argument. So there is an easy way to solve this problem of having two types of different inner products, and that's to call them differently. Okay? So the maths version, I call it A, B, as I've been doing in the videos, while the physics version, I just call it A bar B. Okay? And they are the same thing except for swapping the first and second arguments. So you could say that A bar B is equal to B, A. Yeah? So that will be the only difference. Okay. Now, thanks to having an inner product defined, this allows us to define different properties about vectors. For example, so this is what I call definitions associated to the inner product. For example, the norm of a vector in general can be given using the inner product. So the norm of a vector v is defined as the square root of the inner product of a vector with itself. And that's a definition of the norm. Another way to write this would be to say that the norm squared equals the inner product of the vector with itself, of course. Yes? So for example, let's say we are talking about vectors in 3D. Then an example of inner product A and B is given by the dot product of A with the complex conjugate of B. Okay? So therefore, this means that the norm of A squared is the inner product of A with itself, which is equal to the dot product between A and A complex conjugate. And that's a way of calculating the norm of a complex vector. Okay, another definition that the inner product allows us to do is to define orthogonality between vectors. So we can say that A and B are orthogonal if and only if, and this is by definition of orthogonality, this is what we define it to be, when the inner product between them equals 0. Yes? So that's how we can tell if two vectors are orthogonal. Okay, next you saw that there are many useful applications for the inner product. For example, orthogonal, the concept of orthogonal and orthonormal basis. So you learned that a basis, let's write the basis, E1, E2, up to En. This basis is an orthogonal basis if and only if the inner product between any two vectors is equal to 0, as long as the vectors are not the same vector, as long as I is different to j. Yes? So this means that every vector is orthogonal with respect to every other vector in the basis. Yeah? So for example, x hat, y hat, z hat. So the inner product between any of the pairs, x hat with y hat, or y hat with z hat, or x hat with z hat, all the three possible pairs, the inner product between them is 0 because they are all orthogonal to each other. Therefore, the basis is orthogonal. Yes? Now, a basis is orthonormal, and now we can use hats to denote the vectors in the basis. So a basis is orthonormal if and only if the inner product of a vector ei in the basis with a vector ej in the basis is equal to 0 if I is different to j, which is the same as saying that the basis is orthogonal, and it's equal to 1 if I is equal to j. So what does this mean? Let's think about it. If I is equal to j, what I'm doing is I'm calculating ei with ei. So a vector with itself. And we know that from the definition of norm, this is the norm of ei squared. Yeah? And therefore we're saying that the norm has to be 1. That's what this 1 is saying. So this means that in an orthonormal basis, the norm of every vector in the basis is 1. That's why it's called an orthonormal basis. Because every vector is normalized. It has a length of 1. For example, x hat, y hat, z hat is an orthonormal basis. It is also an orthogonal basis, yes? So orthonormal is a more stringent condition than being orthogonal. Yeah? So every orthonormal basis is necessarily orthogonal, but not the other way around. Okay, now this means that if we have an orthogonal basis, it's very easy to find the components of a vector in a basis. So let's say a vector v can be written in a basis using the components v1 times e1 plus v2 times e2 plus dot 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 vn times en. Yeah. So these are the components of the vector. So let's say that we don't know what these components are. Okay. So we know what the vector is and we know the basis, but we do not know the components. This is a problem we solved in the previous questions, and what we have to do is to solve a system of equations. But in general, that can be more or less complicated. So there is an easier way of doing it if the basis is orthogonal, and that's by using a recipe. And the recipe is the following. Vi, so the ith component of the vector in this basis, is equal to the inner product of v with ei divided by the inner product of ei with itself. And this is true if ei is an orthogonal basis. Okay? Now, it's even easier if the basis is orthonormal, because in that case, vi is given by the inner product between v and the basis vector, which has a unit length. And this is true if ei is an orthonormal basis. Okay, we will do some problems later. Then we can use the inner product to do a projection of a vector into a subspace. Okay, so let's see what this means and how we can write it. So let's imagine we have a subspace which is a plane like this. Okay, this is our subspace. Let's call it subspace W, capital W. Okay, and now let's say that this subspace is the span of two vectors, vector e1 and vector e2. So these are two vectors that are in the subspace, yeah, and they span this subspace. Okay, so we could say that W equals the span of e1 and e2. Okay. Now imagine that we have an arbitrary vector v, which is outside of this subspace. Okay, that's our vector v. So the projection of v into this subspace, which would look something like this, the projection of this vector into the subspace, okay, projection of v, let's call it w, okay? So w, lowercase w, is the projection of v onto the subspace given by capital W. So this is the setup of the problem. So there is a very easy recipe to find the vector w, given that you know vector v, vector e1, and vector e2. And the recipe is the following. W is equal to v inner product with e1 divided by inner product of e1 with itself times e1 plus v inner product with e2 divided by e2 inner product with e2 times e2 plus dot 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 up to en. So in general, although in the picture I drew a plane given by two vectors, in the general n-dimensional case we could have n vectors e1, e2, e3 up to en, and we want to project a vector v which is outside of this n-dimensional subspace. We want to project it into this n-dimensional subspace. That's why we need to consider n different terms. And this is the recipe for the projection. Okay? And finally, we can see how to calculate the Hermitian inner product of vectors which are written in an orthonormal basis. Okay, so let's clarify what I mean. So let's say we have two vectors, a and b. And then we have a basis that is orthonormal. So we use hats. E2, En, orthonormal. So what this means is that vector A can be written as a linear combination of n coefficients times the n basis vectors, right? And those are the coordinate, those are the coefficients of vector A. Well, vector B can be written as a sum of coefficients bi, which are in general different, yeah? So we can write the vectors as a linear combination of the basis vectors, yes? And then this means that if we want to do the inner product between A and B, and this I showed you the proof in the video step by step, yeah? But the final result was that the inner product between A and B is equal to the sum between 1 and n of AI BI conjugate, which, if you want to write it without the sum symbol, is A1 times B1 conjugate plus A2 times B2 conjugate plus dot 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 an times bn conjugate. So this is a fast way of calculating the inner product between two vectors when you can express them as the components in an orthonormal basis. For example, if you have two vectors ax, ay, az, and b equals bx, by, bz, in the basis, in the orthonormal basis, x hat, y hat, z hat, then you know that the inner product of a and b is simply equal to ax, bx conjugate plus ay, by conjugate plus b plus az, bz conjugate. Now, you always remember this. You always have to conjugate the second vector, not the first one. Yeah. But what happens if both vectors are real vectors? For example, like we were doing in the last chapter 1.1, every vector is real. Then doing the complex conjugate to a real number is like doing nothing, right? Because the complex conjugate is like changing the imaginary part. But if the imaginary part is 0, you cannot change anything. So then you arrive at saying that the inner product is equal to axbx plus ayby plus azbz, which is what you already know as the dot product. That is because the dot product is an example of an inner product when the vectors are real, so that the complex conjugate doesn't affect the result. Yes? But remember, when the vectors are complex, if you want to do this inner product, you always have to remember to conjugate the second vector. Yes? Okay. So with this, we can now jump to do some problems to put all of this into practice, because there are lots of equations and it's really useful to see some problems to understand everything.